Welcome back to Coffee Breaks. Today, we're venturing into one of the most intriguing and theoretical concepts in astrophysics: white holes. While black holes are famous for their immense gravitational pull, white holes are their mysterious counterparts, often described as the reverse of black holes. Join me as we explore what white holes are, their theoretical foundations, and the fascinating possibilities they present. So, grab your coffee, sit back, and let's unravel the mysteries of white holes together. White holes: a deep dive into the cosmos. Welcome. Today, I'm thrilled to take you on a fascinating journey through one of the most theoretical and intriguing concepts in astrophysics: white holes. If you're familiar with black holes, you're already halfway there. White holes are often described as the reverse of black holes. While black holes are known for their immense gravitational pull that sucks everything in, white holes theoretically do the exact opposite. They are regions in space that expel matter and energy, preventing anything from entering. The concept of white holes. The idea of a white hole arises from the equations of general relativity, the same set of equations that gave us black holes. Black holes were first theorized by Karl Schwarzschild, using Einstein's equations, which describe how mass warps spacetime. A white hole can be thought of as the time-reversed version of a black hole. If a black hole is a point where matter collapses to infinite density, a singularity, and nothing can escape, a white hole is a point from which matter emerges and nothing can enter. Formation and nature of white holes. Now, you might be wondering, how do white holes form? The truth is, we don't really know if they exist at all. While black holes have been observed and studied, white holes remain purely theoretical. Some scientists speculate that white holes could be the other end of black holes, connected through hypothetical tunnels in spacetime called wormholes. Imagine you have a black hole that absorbs matter. The idea is that this matter might be transported through a wormhole and ejected from a white hole in a different part of the universe, or even in a different universe altogether. This would create a sort of cosmic recycling system. Properties of white holes. White holes are characterized by their event horizons, similar to black holes. However, instead of pulling things in, the event horizon of a white hole repels matter. Any object approaching the event horizon would be pushed away by an intense burst of energy and matter. This theoretical property makes white holes incredibly difficult to detect. If they exist, they might appear as extremely bright objects, emitting intense radiation and particles. But this emission would be brief, as the white hole would quickly expel all its matter and energy. Theoretical background and equations. Let's dive a bit deeper into the math. White holes were first introduced as solutions to Einstein's field equations. These equations describe how matter and energy in the universe influence the curvature of spacetime. In the case of black holes, the equations describe a region where spacetime curvature becomes infinite. For white holes, the equations describe a region where matter and energy are explosively ejected. One of the simplest solutions to these equations is the Schwarzschild solution, which describes both black holes and white holes. For black holes, the Schwarzschild radius defines the event horizon, beyond which nothing can escape. For white holes, the same radius defines a boundary beyond which nothing can enter. White holes and the arrow of time. One of the most intriguing aspects of white holes is their connection to the arrow of time. In our everyday experience, time moves forward. We grow older, not younger. We remember the past, not the future. This one-way flow of time is called the arrow of time. White holes, being the time-reversed counterparts of black holes, challenge our understanding of this concept. If black holes represent a region where the future is determined by the past, since matter collapses and can never escape, white holes represent a region where the past is determined by the future, since matter is ejected and can never re-enter. Hawking radiation and white holes. Stephen Hawking, one of the most famous physicists, proposed that black holes are not completely black, due to quantum effects near the event horizon. Black holes can emit radiation, now known as Hawking radiation. This radiation causes black holes to lose mass over time and could eventually lead to their evaporation. Interestingly, this concept of Hawking radiation might also apply to white holes. If white holes exist, they could also emit radiation due to quantum effects, but in a different manner. While black holes emit radiation as they lose mass, white holes might emit radiation as they gain mass. However, this remains purely speculative. White holes in popular culture and science fiction. White holes have captured the imagination of writers, filmmakers, and artists. In science fiction, white holes are often depicted as sources of immense power or gateways to other dimensions. For example, in the television series Doctor Who, white holes are portrayed as the opposite of black holes, with matter and energy spewing out of them. These portrayals, while fascinating, or purely fictional, the true nature of white holes, if they exist, would be governed by the laws of physics and would likely be far more complex and intriguing than anything we can imagine. White holes in the Big Bang. Another intriguing idea is the connection between white holes and the Big Bang. Some scientists speculate that the Big Bang itself might have been a white hole. In this scenario, the universe began as a singularity, similar to the singularity at the center of a black hole, but instead of collapsing inward, it exploded outward, creating the universe as we know it. This idea is purely speculative, but it raises interesting questions about the nature of the universe and the role of white holes in cosmic evolution. If the Big Bang was a white hole, it could provide a new perspective on the origins of the universe and the fundamental laws of physics. White holes in the information paradox. One of the biggest puzzles in theoretical physics is the black hole information paradox. According to general relativity, information that falls into a black hole is lost forever. However, quantum mechanics dictates that information cannot be destroyed. This paradox has led to numerous debates and investigations among physicists. White holes might offer a solution to this paradox. If black holes and white holes are connected through wormholes, the information that falls into a black hole could emerge from a white hole. This would preserve the information, resolving the paradox and providing a deeper understanding of the relationship between general relativity and quantum mechanics. Challenges and controversies. Despite the fascinating possibilities, the existence of white holes remains highly speculative. There is no direct observational evidence for white holes, and many scientists remain skeptical. Theoretical models suggest that white holes would be highly unstable and unlikely to exist in the real universe. Moreover, the idea of white holes raises numerous questions and challenges. For example, how would a white hole form in the first place? What would happen to the matter and energy ejected by a white hole? And how would white holes interact with other objects in the universe? Future research and discoveries. Despite these challenges, the study of white holes remains an exciting area of research. Advances in theoretical physics, particularly in the fields of quantum gravity and cosmology, could provide new insights into the nature of white holes and their role in the universe. Observational astronomy could also play a key role. While detecting white holes directly might be impossible, astronomers could look for indirect evidence, such as unusual bursts of radiation or gravitational waves that could be signatures of white holes. Conclusion. In conclusion, white holes are one of the most fascinating and mysterious concepts in astrophysics. While they remain purely theoretical, they challenge our understanding of the universe and open up new possibilities for exploration and discovery. Whether or not white holes exist, the study of these enigmatic objects continues to push the boundaries of our knowledge and inspire wonder and curiosity about the cosmos. Thank you for joining me on this journey through the fascinating world of white holes. I hope this exploration has sparked your curiosity and provided a deeper understanding of these theoretical phenomena. If you have any questions or want to learn, thanks for joining us on this theoretical journey into the realm of white holes here at Coffee Breaks. If you found this exploration intriguing and want to dive deeper into the wonders of the universe, be sure to hit that like button, subscribe, and ring the bell for notifications on our latest videos. I'd love to hear your thoughts and questions about white holes, so drop them in the comments below. Until next time, keep wondering and keep exploring. See you in the next video.